All right, like I said, we want to learn the potential or the V field of some commonly used objects, and we'll use this later. That's why we're doing it, okay? Oh, I wish. All right, so first of all, a point charge. We talked about point charges when we talked about E field. So here's a point charge, right? Just a charge, okay? And it's a point, all right? It's just a point charge. Now, you just have to take this. You just have to believe me on this one, right? So here's a point charge. If you put a probe charge here, the system will have potential energy, okay? You notice I didn't say it will feel potential energy because that's wrong, right? It will feel a force, but we don't care about that right now. So the system has potential energy. This is the formula for the potential energy of the system. So it's K, our good old friend K, right? The constant, and it's this charge multiplied by the probe divided by the distance between them. All right, so that's the potential energy of the system, okay? Now, okay, that's great, but I want to know the V field, the voltage or the potential, right? No problem, just use the formula. So the potential is just the energy over the probe. So we take this, divide by the probe. You just get KQ over R, right? So that means at this point P, the potential field, or the V field that this guy creates is KQ over R, right? And notice, it only depends on this, and of course, you know where you are, right? All right, so the V field of this guy is KQ divided by the R, and it does not depend on that, because why should it? Remember the stinky fish and all that? Okay. Okay, now notice what's so great about this. Scalars, right? We don't have to do any vector addition. Isn't that great? I hope you think it's great. I think it's great. So what if we have more than one point? Then we just add them. Whoopee! No vectors. So here. So let's say for whatever reason, I don't know, for whatever reason, so I have 5 point charges, and let's say I want to find the potential right here. So you just use the formula, right? KQ1 over R1, KQ2 over R2, KQ3 over R3, KQ4 over R4, then add KQ5 over R5. Ugh. Come on, that's a piece of cake. It's just numbers, no directions. So we just write the sum like that, right? It'll just be lazy, just a sum, you know? So I hope you appreciate that this is far nicer than the E fields, you know? Okay, so there you go. All right, okay, so that's number one, right? That's the number one formula. That's one, all right, so for a point charge, V equals K, I don't care if you use uppercase Q or lowercase q, it doesn't matter. Just like I don't care if you use R or D, it's just the distance between the charge and wherever you are, wherever the probe is, or in other words, where you're measuring it from. Okay, so that's important, right? That's number one important. Now what we want to do is we want to do outside a charged sphere, okay? All right, so here's a charged sphere. It's not just a point, it's a sphere, you know? Charged sphere. So right now we're in the library. So just pretend you're here with us and walk to the Cannon Center, all right? Just walk to the Cannon Center and pretend that you have X-ray vision or something like that, right? So if you walk to the Cannon Center and you look at this charged sphere, what does it look like? Well, you know, it looks pretty small, right? It looks like a point charge, agree? All right, if it looks like a point charge, then what do you suppose the formula is for the potential? Well, it looks like a point, you know, we're outside of it. It looks like a point charge, so probably the same formula, right? Yeah, all right, isn't that great? All right, so at some location P outside, the potential is the same as we have this here. Isn't that great? Life is good. All right, so we have point charge, and then we have outside charged sphere. again, V equals KQ over the distance, R, D, whatever. I'm doing this on purpose, not to get you mixed up, but I want you to be able to recognize it's the same thing as the R, because sometimes some textbooks use R, some textbooks use D, whatever, it's the same thing. Okay, so here's a kind of a nice question. Two chest charges are brought separately from very far away, man, this sounds familiar, huh? Into the vicinity of the charge plus big Q. First, test charge plus little q is brought to point A, a distance from R, from this guy. Next, this is removed, and a test charge plus 2q is brought to a point B. But this is a distance 2r. Compared with the potential of the charge at A, that of the charge at B is what? So basically you're calculating the potential. So this guy creates a potential. You're measuring it here with this guy, right, that far away. And then you're doing the same thing here, right? This guy creates a potential. You're measuring it with this guy, with this probe, but it's 2r apart. So answer the question. Which is what, right? Compared with the potential at A, what is this? Bigger, smaller, the same. So be careful on this one. They're trying to trick you, all right? So pause your video and figure it out. Okay, what does the potential depend on? Does it depend on the charge that created it, or the probe, or both? In other words, does the potential depend on the probe? No! Remember, we divided by the probe. Remember, potential equals energy over the probe, right? So the potential does not depend on the probe. So I don't care if this is plus q, or plus 2q, or plus 2.5q, I don't care, it's irrelevant. But the potential of a point charge is kq over the d, over the distance. Well, here is r, and here's 2r. So this is going to be half as much as this, right? That's all there is to it, okay? So this plus 2q is you call it a distractor. So people who write exam questions, they always put in these distractors. It's things that completely are irrelevant. They try to distract you. You get paid for doing that if you write test questions, all right? So that's the only thing. It depends on the distance from the charge that created the potential. All right, let's go back to this. This is one way of describing a charge. It uses vectors and everything. This is another way to describe a charge. Use scalars. We can use a voltmeter. It's awesome, right? All right, so there are two ways of describing charge. So should this be related to that? Obviously, yes, right? So that's what we want to talk about now, okay? Now, let's go back to our capacitor. By the way, this is called a parallel plate capacitor because of parallel plates, right? Okay. So with our capacitor, we said that the delta V is, the talking horse, right? Ed. Therefore, E is just delta V over D, right? The distance between them. Okay. Now, this formula is generally correct. If this is generally correct, all right? So that's what we're going to use in Physics 105. There's a little bit more to it, but we're not going to worry about it in this class, okay? So look at, here we have the electric field, the magnitude of it, and here we have the potential difference, or the voltage, or the V field, whatever you want to call it, right? So this equation relates this with this. So if you know that and that, you can get that. If you know that and that, you can get that, right? I mean, I'm just saying, the V field and the E field are related through that equation. And that's nice, right? It's nice. Okay, here's a point charge, right? Here's the point charge. And according to this, the potential, constant divided by R. So as you get further and further away, this gets smaller and smaller and smaller, right? But if you just have one particular R, okay, like see here, I don't know if you can see this, but this is a sphere, right? This is a sphere concentric with this. In other words, everywhere along this surface, it's at the same value of R. So everywhere along this surface, there's one value of the potential. So we call it an equipotential surface. Now here's another sphere, right? And everywhere along the surface of this sphere, it's at a different R. It's at a larger R, right? So because of this formula, the potential here will be lower than the potential here, right? And you have an infinite number of surfaces that you can just keep going and going. But all I'm saying is this is high potential because it's small r. This is lower potential because it's big R. Okay, whoopee, right? Now, what did we learn about E-field lines? E-field lines point away from the Q, right? They point away from the Q. Well, look at that. This is, these are spherical surfaces, so that means there's always going to be a 90-degree angle between the E-field line and the surface of the sphere. Yeah? All right. Okay. And something else here. Notice, we'll talk about this later. Notice that the E field always points from high potential to low potential. Okay? So two things that we'll see in lab and we'll talk about later. The E field lines are always perpendicular to the equipotential curves, surfaces, lines, whatever. And the E field line always points from high potential to low potential. It's easy to see with a point charge. And you'll see it in lab. All right, here is our good old friend again. Hold on a second. Yeah, this is just another example of that. So here's a capacitor, right? 1.5 volts, 0 volts. This is high potential. This is low potential. And notice how the electric field, so these are equipotential lines now. And notice how the E field, perpendicular to the equipotential lines, just like with the point charge, and how the E field go from high potential to low potential. Well, no kidding, they go from plus to minus, right? And so it makes sense, huh? All right. Okay, very nice. Okay, all right, this is kind of funny, but so here's another, somebody's imagination about how a battery works. Okay, so again, think of a battery. You're taking those electrons and you're taking them from where they want to be on the ground, and you're right with a negative terminal, and with a positive, no, what did I just say? Yeah, you're taking them, electrons, you're taking them from the plus terminal where they want to be, and you're lifting up to the minus terminal where they don't want to be, so they're gaining potential energy, yeah? Okay, well here's another example of that. So here's like the electrons. So there's little people inside the battery, right? So you take the electrons and you bring them up, right? You raise them up. You bring them up this crazy stairway. So now they're gaining potential energy, yeah? Right? Okay, whatever. Now, this is a kind of important picture. So next chapter, we're going to talk about electrical currents in gory detail. And what we're going to learn is that what really flows through a wire? It's electrons, right? It's electrons. Now, unfortunately, people, when they were learning about currents and electrons a long time ago, they didn't know about electrons, and so they thought that current was something positive that was flowing, all right? But it works, but it's actually kind of nice because it makes the math work out just like lifting weights, all right? So what we do in physics, you're going to laugh, what we do in physics, we ignore reality, okay? And we talk about something called conventional current. All right? So the conventional current is the flow of plus charge carriers. Okay? Now, total garbage. Come on, it's electrons that flow. Who cares? We're just going to always say that conventional current is the flow of positive charge carriers. You'll see later or soon that it makes the math just nice because you don't have minus signs. But it's total garbage, but we don't lie, right? I don't say it's a flow of protons because that would be a pure lie because protons don't flow through a conductor. I say It's the flow of positive charge carriers. Well, there is no such thing, all right? It's in the imagination, okay? So all I'm saying, so here's an example of that. So here's the battery, right? So here's the plus and here's the minus, all right? So what are we imagining? We're imagining positive charge carriers moving away from this because they're repelled, and they're moving towards this because they're attracted, okay? So basically, from now on, when you see an I, that stands for conventional current. It's the flow of positive charge carriers. When we mean electron current, we'll usually do this, or maybe this, or something like that. We'll somehow designate that we mean electron. But you know, it's the same. I mean, the only difference is the direction, right? I mean, who cares? It's not a big deal. If it makes the math work nicely, why not use it, okay? So there. All right. So this is what I'm saying. So just imagine this. So down here you have positive charge carriers, whatever that is, right? Positive charge carriers are at the negative terminal. They're all happy, right? They want to be there, you know? They want to be down here. Leave me alone, right? But then the little people inside the battery, they lift up these positive charge carriers and they put them to the positive terminal where they don't want to be, right? They're repelled, you know, lifting weights. So they don't want to be there. Then as soon as they're there, they say, you're on your own. So where do these positive charge carriers want to be? They want to be down here, right? So they say, I'm out of here. I mean, they can't go back this way because you just can't, sorry. There's people preventing you that, right? And so they just go, I'm out of here. You know what I mean? All right? So they just flow along the wire and they go back to where they're happy. Okay? Now, there's more to it than that. Okay, again, right here, the positive charge carriers have no energy, right? They're on the ground being lazy bums. Then the battery raises them up here so they have potential energy, which is related to voltage, 6-volt battery, right? Then they say, I'm out of here. So they go along the wire, and here's a light bulb. So what do these positive charge carriers do with the light bulb? Well, they light it up. Well, how do they do that? I mean, what does it take to light up a light bulb? It takes energy, electrical energy. So basically, you know, the positive charge carriers have energy right here. They give it all up to the light bulb. And then they just, you know, continue on their merry way, and they have 0 joules of energy here, okay? So that's how it works. So like this thing doesn't eat positive charge carriers, or in the real world, it doesn't eat electrons, right? The light bulb or the CD player or whatever you want to consider doesn't eat charge carriers or electrons. It just uses up their electrical potential energy, okay? So 0 potential, let's talk about volts, all right? So 0 volts, then you lift those poor guys up there, so they have 6 volts, goes through here, gives up to 6 volts, back there to 0. And you know, you can talk interchangeably, you know, energy of volts because they're related, right? I mean, right? They're related. In fact, whenever I think of potential, you know, or the V field, I just think of energy because it's related. Just like when I think of E field, I think of electrical force because they're related. Okay, let's see. All right, so it cracks me up, right? I mean, thinking of, you know, people inside a battery, but it's a really good analogy, you know, just like that escalator. And don't forget the conventional current, and this uses up all the energy or all the voltage, you know, so it goes back here to 0. Okay, let's revisit something we talked about, I don't know, some time ago. I told you we would revisit this. So this is a conductor in electrostatic equilibrium. So just pretend you have a hunk of copper. And electrostatic equilibrium means that none of the charges are moving, right? Equilibrium means no acceleration. Static means no motion. So we went through all this stuff, remember? And let's just concentrate on the first one. The first one says that the electric field has to be 0 within the conductor. Why is that? Well, because of this. Right? If the E field was not 0, then you'd have a force which would accelerate the charges, so you'd have a current. You wouldn't have electrostatic equilibrium, right? So the E field has to be 0 within the conductor. All right, this is great. Now, But you know, we have this equation that relates the E field and the potential, or the potential difference, whatever, right? Okay, so we know that the E is 0 within a conductor. Now, careful. Be super careful now. So, what is true about V? Now notice, I didn't say what's true about delta V. I said what is true about V within a conductor. So think about it. Use that equation. Think about it. Well, I hope you see that if E is 0, that means delta V is 0, right? So delta V is 0. Well, that means that V is what? Constant, right? That means V is a constant. It doesn't change. Okay, see the difference? Right? Delta V and V, you know. Okay, so that means that E field is 0 within a conductor. That's the potential itself is constant inside the conductor. Okay? Now, if this is constant, that means that the electrical potential energy is constant. That means there's not going to be any like current flowing or anything like that, right? Okay, now who cares? Well, so let's say there's a lightning storm. Where would be a good place to hide? Inside a metal car, not outside. Okay, I'm going to touch the thing in here. So why do you want to be inside a metal car in a lightning storm? Well, a metal car is a conductor, right? The E field inside a metal, the E field inside a conductor is what? 0, right? And so even if the lightning strikes the car, if you're inside it, you're going to be shielded. It's not going to be any E field. Potential is going to be constant. No currents, nothing. It's totally safe. On the other hand, if the lightning strikes the car and you are dumb enough to touch it on the outside, well, good luck, you know. All right. Okay, let's see. How do you like this photograph? Does that guy look like Frankenstein or what? I think it does. But anyway, so you can see the lightning strikes the car, and then you can't see it, but you can just imagine the charge is traveling over the surface of the car, and somehow it gets to the axle or something, and then it goes right to the ground, right? But he's perfectly safe, you know. Frankie is perfectly safe inside the car. Okay, let's quit. Yeah, let's quit. Okay, I'm ready. Okay,